Welcome back to Engineering Dynamics. I'm your host, Dr. Walk, and today we are going to be learning about rigid body motions. There is a hurricane scheduled to hit us in a few days, so I'm going to try to get this video out to you guys. So rigid body motion, let's just jump into it. What is a rigid body? A rigid body is when all the particles on one body remain at the same distance. So a classic example is a fishing pole, a rigid body. No, because when you catch a fish, the fishing pole will bend, so it's not a rigid body. During that bending motion, the particles within it will spread apart, right? A rigid body is known to say that, okay, all the particles within a body have the same distance at all times. It's not going to deform. When a rigid body goes in motion, it can have three types of motion. One is translation. Basically what this is that all of the particles on the rigid body are going to move at the same velocity, and omega, the angular velocity, is 0. A really good example of this is if you take an eraser and you put it, like, on the whiteboard, a little eraser track, like where you hold your markers, just push the eraser along the track. That's linear motion. So if I put 2 dots on an eraser, and when I move the eraser, the 2 dots are not going to change distances. So that's going to be a rigid body under pure translation. Then a rigid body can also be under rotation, going under pure rotation. So rigid body undergoing pure rotation. If you look at, say, the blades of this, these are all going to rotate at the same omega about an axis. So now that we're in rigid bodies, particles, they aren't going to rotate. Like, the difference between the two is a particle is just one particle that is going about a path, right? And it's just it's like, it could be a system of particles. Here, let me see if I can draw this. So it could be a system of particles, right? But this particle is not constrained to the motion of this particle. They can have their own omega and their own velocity. It's not constrained in any way. But when you have a rigid body, it is now going to be constrained. Okay, so the motion profile of this particle within the body is dependent. It's constrained based on this one. So say if I wanted this rigid body just to rotate, the whole body, every point in the body is going to have the same omega, but now the velocities are going to be different, because this velocity will be smaller than this velocity, which will be smaller than this velocity. Because as my radial length increases, my linear velocity increases. We also saw that if you were in the class that I talked about this, when we talked about acceleration, we said that as you move out like this, your linear velocity will increase as your radial distance increases, while your omega stays the same. It's the same thing here. So each particle could be different, but on a rigid body, no. Okay, so say we have a rigid body here, and I'm just going to put this rigid body in pure rotation. So this here would have a linear velocity of nothing. Okay, we can call it 0. Okay, and inside this rigid body, you have several different particles. Now, the particles, they are all going to undergo the same omega, and we can call that omega, like, what should we, that point is labeled 0. So maybe we're going to call this rigid body, we'll name it B for body. So the body will undergo some rotation. So that means that all these particles will have the same rotation. So now I'm going to say, okay, well, I want to know, from looking at this point, since this point is not like rotating or anything like that, I can make this a reference frame. So, and it's an inertial reference frame because it is not translating or rotating. So this is my X, this is my Y, and I can locate a few different points. So let's locate this one, and let's locate this one just for our demonstration. So I'm going to say that R, and we can label this 1 and 2. So if we look at the linear velocity of 1, the linear velocity is always perpendicular to its position vector. So the velocity of 1 will equal omega B cross R1 with respect to O. Okay, so this could also be respect to O if you want, or you can write it as this. It's the same thing. Okay, now you're also, this velocity one is going to be smaller or bigger in magnitude if we said the velocity of 2 relative to O is equal to cross R2 with respect to O. The velocity of point 2 will be smaller because its R magnitude is smaller than this magnitude, and omega B is the same. So this R really has an effect when it comes to rigid bodies, which we don't see in particles. Okay, so these V's will be different. So that's just something heads up on rotation when it comes to pure rotation. The third type of motion that your rigid body can experience is called planar motion. I've also seen it called complex motion, but basically what it is it's the combination between translation and rotation. So for our rotation, we said that V equals omega cross R. Okay, that is a body that is in pure rotation. But if we have a planar motion, that means that you're going to have rotational motion and you're going to have linear motion. So that kind of looks like, if you think of a wheel and like a tire on a car, think about that and think about it rotating and translating. So we have one that is, say like the first one, you hit a piece of ice and you just slide. There's like no rotating, you're just sliding. Then you have pure rotation. Those two added together is going to equal your planar motion. So let's work that out. I don't think for the eraser, I did say it, I just didn't put an equation to it. So I said if you had 2 points, A and B, on the eraser, they would move at the same linear velocity. So let's use an example here. We have a wheel, and the wheel is rotating about its center point, but it's also traveling along a road. Okay, so it's moving here, but it's rotating about here. So this is going to be omega of the wheel, and it's moving at some velocity V. And I want to say, well, because there's a bunch of particles within here, right? But I want to compare, say, point A, and I want to compare it to point B. And I'm picking two random ones. I can say velocity of A is equal to VB plus omega cross RA with respect to B. So I can say that, look, the velocity of A is going to have the same amount of velocity of B, but it's going to also have a rotational aspect to it. And that's going to be, if I'm looking at, and I can draw a little vector here, I'll make it a pink. So I can say, okay, I'm looking at vector A relative to B. So in this moment, I'm saying that A is rotating about B, because if I'm sitting on B, my viewpoint, B is not moving. So if I'm looking at A, it will have the rotational aspect here. So, okay, so let's do our first example problem. We have a rack and pinion, and what is the rack, or the pinion, excuse me, is rotating about point D, and as it rotates, it's going to pull that rack down. So we're given that AB, which kind of looks like a crank at this point. It's cranking. It is cranking downward, which is going to push the, if you move it this way, it is going to push C this way. So C, it looks like it's going to push C this way. So this gear will go this way, which means this will go that way, right? Okay, so before we start the problem, I just want to understand what's happening, okay? So again, this is acting like a crank. So B is in pure rotation about A. B is in pure rotation about A. And in mechanics, we call that a crank because it's just going around in a circle. Now, B and C, what type of motion is BC undergoing? It's undergoing planar. So if B is in pure rotation about A, it undergoes pure rotation about A. Okay, so we can say that point B is in pure rotation about A. Okay, so now I want to know, well, what is B? B and C. B is also on a rigid body, BC. And BC is undergoing planar because BC can move this way, but it's also going to be rotating. Okay, so it's got like a little bit of a weird motion going on. What about now C is also attached to the rigid body CD. What is rigid body CD undergoing? Well, C is actually going to be in pure rotation. So C is in pure rotation about D. And then what is, if we make, there's another point in contact here that is kind of of interest to us. I can label that E. What is point E doing? E is a part of D and it's a part of this linear rack. So E, there will be a connection point here, and we can say that E, if we're looking at it relative to the rack, will be in pure translation. If we look at it relative to D, it will be in pure rotation. So ED, pure rotation. But ER, because this is a rack, so we'll say that's R, is in pure translation. Okay, so that's kind of what we're looking at. And we're asked to find, well, what is VR? Well, VR will equal VE in the J direction. And I'm picking J because, well, you can pick anyone you want, but we're going to make a reference frame. And I'm going to pick a Cartesian reference frame. I'm picking that because we have rotation and translation, and I am given lots of different measurements that are horizontal and vertical. So I'm just going to say that this is Y and X, and this movement, this rack, is going to be moving downward at some velocity that I'm trying to find. So that is going to be in the J direction. Okay, so I'm looking for this. Well, if this equals that, I need to find that. Well, what does that equal? Well, E is in pure rotation to D, I said. So I can say that VE is equal to the pure rotation of D. So this would be omega D cross. Now we have to say, well, I'm looking for the velocity of E. Velocity of E would be tangent to the curve and perpendicular to its position vector. So I'm looking at a velocity vector. So this position vector that's perpendicular here will be RE with respect to D. Trick. If the letter here is E, the top letter has to be E. So whatever letter is here, the top has to be. Okay. Okay, so, all right, well, that's fine and dandy, but now that gives me another unknown. Now I'm introducing an unknown of omega D. How do I find omega D? Well, I could relate it back because D is a part of C. So I could say, okay, velocity of point C is equal to omega D cross RC with respect to D. So now I have a vector. I have a vector pointing to C like this. So this is RC with respect to D. And I want to know what its velocity vector is. So that's going to look something out like this. This is the C because it is perpendicular to the position. Well, crap. I still don't know omega D because now I have another unknown, which is VC. But VC is also on another rigid body. We said VC is a part of VB. So I can say that VC also equals RC with respect to B. So now I have VC, I have another vector here, and this is going to be RC with respect to B. So VC is still going to be in this direction. It's not, you can't do a perpendicular velocity here because this is an impure rotation. It's planar, so you can't just add another V. This is still velocity of C. But now I have to say, well, what omega is it? Well, it's going to be omega C or BC because it's going to be whatever that omega is. Well, man, so I still have two unknowns. I don't know what that is. Oh, and what did we do wrong here? What did we forget? VC is not a, because we have two equations here and two unknowns, but this isn't correct. Because it's undergoing a planar is undergoing planar motion. So let's think about this again. What's the planar? Planar has, it is VC equals, and it is omega BC cross RC with respect to B, but it is also moving at a linear velocity. So let's look at B. B will have a linear velocity because it's in pure rotation here, so I can draw that because its position vectors here. Oopsies. Its position vectors here. These are perpendicular. So this would be RB with respect to A. You have to include its linear velocity here. So now I have 2 equations, but I have 3 unknowns. Okay, so let's do one more relation because we did say that B is on the rigid body AB. So B is in pure, we said was in pure rotation. So I can say that VB equals omega AB cross RB with respect to A. Hey, and guess what? We're given this. We know this. We can find this. Plug it back in here. 2 equations, 2 unknowns. We can find omega D, and then we can plug it in here, and we're done. So, and I know this seems crazy, but the more you do it, the better you're going to get at it, and you'll be able to do it fast, okay? But this is the way it's going to be done. So I want you to start with this. This is going to be equation 1, 2, and 3 you're going to work together with. 4, and then you can VE and VR are the same. Start with our first equation. VB equals omega AB cross RB with respect to A. And VB is what we're looking for, so I don't know that. But I do know omega AB. Omega AB was given to us as 10 radians per second. It's going clockwise, so it's going to be a negative 10K cross RB with respect to A. So RB, if I project this down this way, it's going to be 6 in the I. And it's going to be 12 in the J. So VB will equal, if I do 10, that would be 60J. So I'm going to have 60J, and I'm going to have 120I. And my J will be negative. If you don't know how I did that, then we need to go back to cross products, and we do I, J, K, and then the signs like this go above it. And then I put up my first vector, which is 0, 0, 10, negative, 6, 12, 0. For the first one, I'm going to bring the plus in the I, and I'll do 0 times 0, 0, minus negative 12 times 10, which is 120, I. And then I'm going to do that for the second one. I bring down the negative and the J, and then I cover this one up, and I do 0 times 0 is 0, minus 6 times negative 10, which is going to be 60J. Okay, so just if you needed a quick review of that. All right, so this is equation 1. Okay, let's go ahead and do our VC equation. Our VC equation is going to be VC equals VB plus omega BC cross RC with respect to B. VB, just plug in here. So that makes VC equals 120I minus 60J. Plus, I don't know the magnitude of omega BC, but I do know that it's in the K direction, and I also know that it's in the clockwise direction. I know that because this is moving this way, and this would have to be pushing down in order for this to be rotating. So I kind of do know the direction of that. And then I'm going to say cross RC with respect to B, and RC with respect to B. So RC with respect to B is going to go over 16 and down 2. So over 16, down 2. So this is going to be VC equals 120I minus 60J. And I'm going to say K cross I. So that's going to be minus 16 omega BC J. And then I'm going to say K cross J, which would be minus 2 omega BC I. Okay, so now I'm going to so this is our equation 2. Now I have to do a different expression for VC. VC is on 2 rigid bodies. C is connected to rigid body BC and CD. C is in pure rotation relative to D. So I'm going to use our equation that we made up here, our pure rotation. So VC equals omega D cross RC with respect to D. VC will equal omega D is, again, we don't know the magnitude, but we do know it's it is clockwise, excuse me. So it's clockwise in the K direction, and it is going to be crossed C with respect to D. So that's going to be a -6 inches and a +10. So -6, +10. Okay, so we have VC equals K. So I'm doing this in my head. I don't know if that's confusing people or not, but I kind of use this method along with this one. And I'm going to do K cross I, that's positive, and we have two negatives, which is also a positive. So I'm going to have +6 omega D in the J. And then I'm going to have K cross J, which is negative, but you have another negative there, which is going to be +10 omega D in the I. So this is my equation 3. Now I need to set 2 equal to 3. So I'm going to have 120I minus 60J minus 16 omega BCJ minus 2 omega BCI. And I'm setting that equal to 6 omega DJ plus 10 omega DI. One vector equation that has 2 units in it is actually going to be 2 scalar equations. So I'm going to gather up my i's, and I will make that equation first. I'll have 120 minus 2 omega BC equals 10 omega D. And I can go ahead and solve for omega D here. So omega D is going to equal 12, and then divide this, it'll be 2 divided by 10 omega BC. Okay, and then I can calculate my my next set of terms, and I can say my J terms, it's a little thick, it's going to equal -60 minus 16 omega BC equals 6 omega D. And I'm going to plug in my omega D here. So I'll have -60 minus 16 omega BC equals 6 times 12 minus 2 over 10 omega BC. So it's going to be -60 minus 16 omega BC equals 6 times 12, which is going to be 72 minus, so 6 times 2/10 would be 1.2 omega BC. So I'm going to subtract 72, and I'll get -132 equals, I'm going to add the 16, so that's going to be -1.2 plus the 16, which would be 14.8 omega BC, and then -132 divided by 14.8, I'm going to get -8.9 radians per second. And then I'm going to, so this is equal to omega BC. I need omega D. So I'm going to back substitute this into here. So I'm going to say omega D is equal to 12 minus 2/10, -8.9. And I'm going to get, which is going to give me 13.78 radians per second. Okay, so let's look at what these signs are telling us. It's telling me that I did guess omega D to be negative. So that's right on my drawing. But this, it says that it came out as a negative, which means that it's actually rotating in the opposite direction of what I assumed. So this is actually rotating that way. Okay, but it doesn't matter what you guess because math makes it work, right? So now that we have omega D, I can then go to my last equation, which is VE. Velocity of E, which equals the velocity of the rack, equals omega D cross R E with respect to D. So my velocity of my rack is going to equal 13.78 K, and that's happening in the clockwise direction. cross RE with respect to D. So RE with respect to D is going to be 6 inches in the I. And I'm going to do K cross I, which is positive, but you have a negative here. So that's going to equal negative in the J direction. And 13.78 times 6 is 82.68, and that's inches per second. And then if we wanted it in feet per second, just divide by 12, and you would get 6.89 feet per second in the negative J direction. Okay, so that was an example of, it had rigid body motions in it. It had a pure translation, it had pure rotation, and it had planar motion. So I hope that helps clear up why we use relative motion and how to use it. Until next time.